Thank you so much, Paul. I hope you see my screen okay.
Yep.
Perfect. Yeah, so today I will tell you a little bit more about temperature variability projections and whether we can constrain them to good historical performance. And understanding how this temperature variability changes with warming is quite crucial to determine how extreme events or their intensity and their frequency might change in the future. And also things like the temperature range, ecosystem, and societies will need to adapt to with warming. However, these changes remain highly uncertain. Models disagree on the magnitude of temperature variability changes, but they also even disagree on the sign of these changes under warming. So our question is, can we reduce these uncertainties in the future variability changes by constraining model projections to only those models that capture historical variability correctly? So what we want to do is this performance constraining based on all available single model initial condition ensembles from CMIP 5 and CMIP 6 against observations. And to do this, we will use a rank frequency analysis framework that I will explain to you in a second. So as I was saying, this rank frequency variability analysis will be the basis of our evaluation. And what this really means is based on a very simple concept. So if a model captures observations accurately, this means observations should fall distributed uniformly across the whole model spread. Or what means the same with uniform frequency across all the ensemble ranks, exhibiting a flat rank histogram. What we call a rank here is just how for example, the ensemble members are ranked by ascending temperature values here. As you see here, surface air temperature for the summer. So the member with the lowest temperature will be rank 0, and the higher member will be rank 50 in this case as the number of members. So whenever we have this condition fulfilled, you will have a fairly flat observational rank histogram. However, how much non-flatness is okay for a model that still captures observation as well? We introduce here a perfect model rank evaluation, which means we treat each member in a model ensemble as if we were observations, and we do the same process. We see with which frequency it takes each of its ranks, and then we do this for all models, creating a range of sort of flatness or rank histogram frequencies. There is okay, meaning that if observations rank histogram falls within this range, within the perfect model, the differences between the modern observations can be explained by just the short observational record or internal variability alone. Versus when observations fall outside of this perfect model range, we have a clear disagreement between the model and the observations for a particular region, and the model does not capture observations right. So as you see, it's quite an easy and straightforward concept, and what is important is that it's not making any assumptions about what the shape of the distribution should be, what the observational sampling details, anything like that. So it only says the model should be, or the observation should be distributed uniformly across the model. So using this rank frequency analysis, we evaluate all these 11 models across land and ocean regions globally. And we have different possible evaluation results. So the first one being the model performs correctly, and the other two explore a different set of biases that I will go into in a second. So first of all, the first possible evaluation result is the model does well, as I was saying, and this translates in a flat rank histogram, meaning that observations take all places across the ensemble spread with uniform frequency. And this translates then to the observational variability being well captured by the model. It does not mean that observations are always within the model spread, quite importantly. It is fine that observations fall outside of the spread as long as they do so with the appropriate frequency. The next type of situation that we can find is where observations cluster within the central ensemble spread too frequently. And what this presents is a rank histogram that is no longer flat, is rather mound shape or concave. And what this means is that observations take the central ranks in the ensemble with too high frequency, and the model overestimates the observed variability. And then the last type of bias that we can take is a little bit more complicated. It's just reflecting the situation where observations fall outside of the ensemble spread. So in this case that you see here, observations are detrended in this case in the model as well. So observations falling outside of the ensemble spread means that the model underestimates the observed variability, and then it takes this minimum rank and maximum rank with too high frequencies. However, for non-detrended data, so just observations as we see them in the time record, this can also mean that there is a trend under or overestimation biases, meaning observations were within the model spread for a period, and then as warming continued, the model might have warmed up faster or slower than observations, and observations tend to fall below the ensemble. So do not confuse one bias with the other. For the assessment that we're doing here, which is after variability itself, we're using only detrended data to really isolate the variability underestimation data. So this is just the 4 biases that we will see at a glance. And as I was saying before, whenever models capture observations well, we have observations within this perfect model range. And that is highlighted here as the star that you see there at the top. So we will take all of these regions globally where models do well, or the models that do well over these regions, and consider them performing well historically, and select them for our constrained example. So we do this, as I was saying, for a host of regions over land and over the oceans for 2 seasons, for local winters and local summers. And we do this for 11 models across the CMIP 5 and CMIP 6 host. And this is what you see here. So in the rows, you see the different areas. The columns are the different models and seasons. And wherever you see either green or gray shading, it means the conditions that we just saw before are fulfilled. So the observationals rank histogram falls within the perfect model range, and any differences in the time series of observations and the models can be explained by general variability. Wherever you don't see this shading, so the white cells, the condition is not fulfilled. However, we also want to note that this assessment that we did just before was for a time series average over a large area, right? So we don't want to, by doing this regional average, to smooth out any local biases at the grid cell level. So we also repeat a similar but a bit simpler assessment at the grid cell level, and we only consider regions to be simulated adequately if at least 50% of that region's grid cells do not exhibit any biases, and those are the regions here that you see in green. So of course, a lot of information. If you're looking at any particular model or region, I welcome you to go into the paper and see this in a bit more detail, but just a high level takeaway message from here. We find that the models that best simulate the historical temperatures that we've observed are CSM, the CMIP 5 version, CSM2, the CMIP 6 version, and GFDL SPERMET for isolated variability alone, what you see here, the trended time series. And if you're instead interested in just the time series as observed with both the variability and the force trends, then the picture is quite similar. So CSM 1 and 2 are still the best performers, followed now by MPIGE 5, the CMIP 5 version. Also notable to say, the performance is quite a bit worse for both variability and force trends included, which is a harder test to pass, but just to bear in mind that it's really a check worth making to see how well your model or the models that you're considering behave. So now that we have these results, as you see here, all of these green cells that I was saying before, we take for each particular region and season all of these models that perform well and use them to constrain future temperature variability projections. And this is what you can see here. So this is just an example now for a season for a region in Eastern North America. What you see here is the temperature variability change with respect to 1 degree of global warming. And we will do this across all the 11 models for the full ensemble that you see here in black, and the constrained ensemble that you see in this case in blue, but that's gonna take a few different colors. So what this plot tells us is that these thin lines represent all of the spread across all of the estimates in the 11 models in the full ensemble, and in the constrained ensemble models, which are highlighted at the top in brackets. So for each region is going to be a different number of models, and the spread is lower because there are fewer models, or you would expect it to be smaller, sorry. So the thin lines is the full ensemble spread, and the thick lines here, so the thick line in the middle is just the central percentile of the intermodal spread. And then you also see these bars here that highlights the full and constrained ensemble mean difference with respect to 1 degree of warming. So this first point at 1 degree is the baseline for differences. And whenever this bar goes down, means the difference is negative or positive if it goes up. So now that we've explained how to read this temperature variability projection plots, we'll see them for a few selected regions. Again, if you're interested in any region in particular, I welcome you to look into the paper results, which is quite complete. But here I only highlight now 3 types of results. The first at the top is more or less what you would expect. So this means we find a number of regions where indeed the full ensemble of 11 models show some models that do not perform well. So we identify a sufficiently large number of models that perform well historically. And when you look at projections of only those models as so accurate representation of the historical temperature variability, you have less spread in the projections, meaning that by understanding or by taking the models that understand the past a little bit better, you can make better projections of the future. Great. This happens for around half the regions that we look into. However, for many regions, we find a large enough numbers of models that perform well and kick out the ones that do not perform as well, yet the constrained spread in projections is not reduced. In some cases, it's even increased by the central percentile being wider than for the full model spread. So you can see this here in this red box. So for these regions, we indeed find models that perform well, yet these models still largely disagree in future changes on temperature variability, both in the intensity and again, in some cases, even in the direction of change. So performing this constraint to whatever the past tells us is not sufficient to reduce the uncertainty towards the future in these regions. And lastly, we find a third category of regions, which is again quite worrisome, where we find historical variability is captured poorly by most models, to the point that only 1 or 0 models capture the observed time series well. And this happens in regions that are quite crucial for future projections and quite vulnerable at times as well. So regions like Australia, India, South America, Africa, particularly in the local summer of these land areas, and also over the polar and the southern oceans. And this is quite important because, as you can see, these are regions highly populated, also often made of vulnerable populations and of great ecological importance. So we are likely misrepresenting future temperatures, future changes in temperature variability in these areas. And generally, it doesn't happen over all regions, but it happens over most of the land regions. What we find is an overestimation of the current day variability of these areas by most models. That's why they perform badly. And what this means is that if you take this overestimation of the current change compared to a rise that maybe is not as high in the full ensemble, what the constrained ensemble is showing instead is lower variability today going towards a large change in the future. So in these regions, we find generally that if you just take the full multimodal ensemble mean as your estimate, you're largely underestimating future variability change. And with this, I want to just to give you a few summaries of our results. But again, this is quite an in-depth assessment over many regions of the world, and we explore a bit over different regions why these discrepancies might happen. So if you're interested in a particular model or in a particular region, I really would like to point you into this direction of the paper, because I think it's quite useful, especially if you don't want to spend the time to look into all of these regions, all of these models for your study. So what we find is that our models, both from CMIP 5 and CMIP 6, that truly perform better than their peers, with some models that are very widely used performing quite poorly generally. So if you're shopping for a model, take a look and make an informed choice. The second thing that I want to highlight is that constraining projections to past historical performance yields the expected result of improved agreement over some regions, but over many others, it does not. Either because we don't find models with enough, well enough performance, or because even if you find a large enough numbers of models with a good performance, the future projections are still extremely uncertain. So we want to highlight that this is quite an important point. So we have sort of a flavor of model uncertainty that is non-reducible based of the base available information that we have right now, and means that even if you consider these models to be performing correctly right now, they still show very different features. So we cannot really get rid of them and expect to sample future projections adequately. So we really need to keep this multimodal perspective that CMIP offers, even if we inform our models better based on past projections. And I also want to say that particularly in the areas where we find poor simulation, we find that it's actually sort of the full ensemble estimate is actually too conservative, and it underestimates future variability change by quite a bit. So this is just conclusions a bit more targeted to the analysis that we did in temperature variability projections, but I also want to highlight that this evaluation framework is quite simple and approachable for all the metrics. So it allows you to simply and robustly assess model performance without making any assumptions of the underlying distribution, and without having to have very perfect information about the internal variability sampling either, or having a record that is too long. So I would really recommend you to take it up because, as I say, it's quite simple, and particularly combined with this perfect model approach, which really provides an accurate baseline to distinguish discrepancies between model and observations that might be explained just by the limited internal variability sampling. I also want to say, if you're not interested in taking up an evaluation like this because it's quite extensive, and you just want to look at what models perform better for your region, as I said, you have all of the details. I will put it up in a second, how you can access them. And both of these frameworks for evaluation, as well as the performance constraining, can be really applied for other variables and metrics. So if you're interested in that, I will be very interested in collaborating, especially now as CMIP 7 is around the corner. So it will be quite nice to expand it. And here I just leave you with some access links for the article and for the supplementary information, where all of this evaluation is for all of the models and all of the regions. And with this, I thank you for your attention.
Thank you, Laura. Because we've just got a couple of minutes, I thought there's a question here from Francisco Dobles Reyes. So I'll just read it out. He says, thanks for illustrating the use of rank histograms with climate change simulations. Weather and climate forecasters have used for a long time tools like rank histograms, not only to constrain ensembles, but also to design their forecast systems. How can these tools be adapted by climate change modeling scientists to improve the ensemble design?
Yeah, I mean, I've been preaching for the use of rank histograms for quite a while now. Indeed, our inspiration was, in my case, from the seasonal decade and forecasting communities, which was done at the institute where I started doing this quite a bit. But yes, in this is a very widely used tool for forecasting of any type, particularly combined with this perfect model range that we have available along the CMIP host of models. I think this is really quite powerful and could be taken up for evaluation of metrics across the board. So I'm advocating for it to be taken up, Francisco, and we can gladly join forces. I think it's really a great and very simple method.
Okay, thanks, Laura.